Hello everybody. In this video we are going to be looking at the solutions to the honors mirrors homework problems 6 through 10. Well, let's take a look at problem number 6. If you look at yourself in a shiny Christmas tree ball with a diameter of 9.0 centimeters, when your face is 30.0 centimeters away from it, where is your image? Is it real or virtual? And is it upright or inverted? So if this Christmas tree ornament is acting like a mirror, it is going to be a convex mirror because the reflective surface is on the outside of the curvature. So it's a convex mirror. The diameter of the mirror is 9 centimeters, and we'll explain the negative sign in just a second. If the diameter is 9 centimeters, the radius of the curvature of the mirror or the Christmas tree ball is going to be half the diameter. So 9 centimeters divided by 2 is going to give me negative 4.5 centimeters. And because of the radius of curvature or the center of curvature is going to be behind the mirror because it is convex, that is why we have a negative sign in front of the diameter and the radius. Now to find the focal length of this mirror, and the focal length is half of the radius of curvature. So negative 4.5 centimeters divided by 2 is going to give me a focal length of negative 2.25 centimeters. The object distance is 30 centimeters, and we are looking for the image distance. So we're going to start with our mirror equation, and we are solving for the image distance. So solving this equation for image distance is going to give us this right here. And we should be used to using reciprocals because we did a lot of this when we talked about series and parallel circuits. So remember, if we did series and parallel circuits, we used formulas that are very similar to this. Same kind of concept here, same kind of math. The one thing that you have to be careful of, though, is always remember to take the reciprocal of all the reciprocals. So that is going to be equivalent to that reciprocal right there. So you just have to remember to take into account that, that the unknown is a reciprocal as well. So once I plug my values into this equation, I am going to have an image distance of negative 2.09 centimeters. And because this is negative, I have a oops, I didn't do that in highlighter. Let's try that again. Because this is negative 2.09 centimeters, that tells me that the image is behind the mirror and it is virtual. Now, to find out if it is upright or inverted, first thing I want to do is find the magnification of the image. And to find the magnification, I know the magnification is the negative of the image distance divided by the object distance. So I plug in my values for image distance and object distance into my equation, and I am going to have a magnification of 0.070. And because I have a positive value for the magnification, that tells me that my image is upright. Problem 7. A mirror at an amusement park shows an upright image of any person who stands 1.4 meters in front of it. If the image is 3 times the person's height, what is the radius of curvature? So in this problem, we are given the object distance, which is 1.4 meters. We are given the magnification of positive 3, and we are looking for the radius of curvature. And by the way, we know that the magnification is positive 3 because it is an upright image. So because the image is upright, I know the magnification is positive. So I don't give you a lot of information in this problem, but what else can we find? We can't find the radius of curvature directly, so we need to find some intermediate value that will lead us to the radius of curvature. Well, if I have the object distance and the magnification, I can use my magnification equation to find the image distance. So taking my magnification equation, solving it for the image distance is going to give me the image distance is equal to the negative of the magnification times the object distance. So I plug my values for magnification and object distance into that formula, and that will give me an image distance of negative 4.2 meters. So now I have my image distance, I have the object distance. From those two, I can now use the mirror equation to solve for the focal length. So if I want to solve for the focal length, then once again, oops, again, I'm not using my highlighter. I must have something against the highlighter today. So when I solve for focal length, remember I have to take the reciprocal of the sum of my reciprocals. So once I plug my values for object distance and image distance into this equation, that is going to give me a focal length of 2.1 meters. The radius of curvature is 2 times the focal length, so I just have to take my focal length, multiply that by 2, and that will give me a radius of curvature of 4.2 meters. Problem 8. A dentist wants a small mirror that, when 2.20 centimeters from a tooth, will produce a 4.5 times upright image. What kind of mirror must be used, and what must its radius of curvature be? So as with the last problem, we are given the object distance, which in this case is 2.20 centimeters. We are given the magnification, which is positive 4.5, and we are looking for the radius of curvature. The first thing that they want us to do is identify what type of mirror must be used. So in order to produce an upright image with a positive magnification, we have to have a concave mirror. And the object distance must be less than the focal length of the mirror. In other words, the object has to be within the focal point or inside the focal point of the mirror. So if I want to find the radius of curvature, again, I can't find it with the values that I have given, but I can find the image distance if I use the magnification equation. So taking my magnification equation and solving that for image distance, like I did in the previous problem, is going to give me a magnification of negative 9 point, or I'm sorry, it's going to give me an image distance of negative 9.90 centimeters. Now that I have the image distance, I can use that and the object distance to find the focal length. And using my mirror equation, solving that for focal length will give me a focal length of 2.83 centimeters. To find the radius of curvature, I know I need to take my focal length and multiply that by 2. So 2.83 centimeters times 2 is going to give me 5.6 centimeters. So that is my radius of curvature for this mirror for my dentist. Problem 9. Some rear view mirrors produce images of cars behind you that are smaller than they would be if the mirror were flat. Are the mirrors concave or convex? What is the mirror's radius of curvature if cars 20 centimeters, or I'm sorry, 20 meters, the car is 20 centimeters away, you got problems. If the car is 20 meters away, appear 0.33 times their normal size. All right, this is going to be very similar to the previous two problems. We are given the object distance of 20 meters. Why do I have centimeters on the brain? The object distance is 20 meters. The magnification is 0.33, and we are looking for the radius of curvature. So I know that to find the radius of curvature, I'm going to need to know the focal length. And in order to find the focal length, I need to find the image distance. And to find the image distance, I need to use the magnification equation. See, not only a few steps here. So, using the magnification equation to solve for the image distance as we've done previously, I know that the image distance is going to be equal to the negative of the magnification times the object distance. So, plugging my values for magnification and object distance into this equation will give me an image distance of negative 6.6 meters. Now I can take that image distance and my object distance, plug that into the mirror equation, solving that for focal length. And when I put those values into the mirror equation, I am going to have a focal length for this mirror of negative 9.8 meters. Doubling the focal length, which will give me the radius of curvature. So doing that is going to give me a radius of curvature of this mirror of negative 19.6 meters. And because my focal length is negative, I know that my mirror is going to be convex. And I also should know that convex mirrors are the only type of mirror that will produce an image that is both upright and reduced. Problem 10. A luminous object 3.0 millimeters high is placed 20.0 centimeters from a convex mirror of radius of curvature of 20.0 centimeters. A, show by ray tracing that the image is virtual and estimate the image distance. B, show that the negative image distance can be computed using a focal length of negative 10.0 centimeters. And C, compute the image size. So let's take a look at the ray diagram first. And I have the ray diagram shown here. So we're looking at this ray diagram. Remember, we know how to draw 3 rays, and I'm going to go over how to draw each of those with you here. The first ray, and this is the one that I have highlighted in red, in the first ray, my incident ray, which goes from the tip of the arrow to the mirror, the incident ray is parallel with the principal axis. When it hits the mirror, it's going to reflect off at an angle, and my reflected ray is going to be lined up with the focal point. Now, the reflected ray doesn't actually go through the focal point because the focal point is behind the mirror. And remember, light doesn't pass through a mirror. That's the whole purpose of a mirror. It's to reflect light, not let it pass through. So my reflected ray doesn't actually go through the focal point, but it's lined up with the focal point. So that is the first ray. My incident ray is parallel with the principal axis. The reflected ray is in line with the focal point. All right, let's take a look at the next ray, which I have highlighted in green. So we're going to do this green one next. In the second ray, my incident ray is lined up with the focal point. So my incident ray is lined up with my focal point. If I trace the incident ray all the way back behind the mirror, it would go through the focal point. So the incident ray is lined up with the focal point. My reflected ray is parallel with the principal axis. So my second ray, incident ray lined up with the focal point, reflected ray parallel with the principal axis. The third ray that I want to show you, and that's the one I have highlighted in blue, if my incident ray is in line with the center of curvature, now again, it doesn't go through the center of curvature because that is behind the mirror, but is lined up with the center of curvature, it's going to strike my mirror at a 90-degree angle, and according to my law of reflection, it's going to reflect back on itself. So those are my 3 rays. Now I'm just going to redraw my 3 reflected rays. So I have one reflected ray, the blue one, going off like this. I have the green reflected ray going off like so, and the red reflected ray like so. Now, if I trace each one of those reflected rays behind the mirror, if I extend those rays behind the mirror, they're all going to converge at one point, and that point at which all 3 of those rays converge is where my image is located. So my image is located right here. So that is where my image is located. Now, because it is behind the mirror, I know that it is virtual. And if I want to estimate the image distance, if I look at how far my image is from the mirror, and I look how far my object is from the mirror, I would say that the image distance is maybe about, a little less than half of what the object distance is. So if my object distance is 20 centimeters, my image distance should be something less than 10 centimeters. Then again, that's just an estimate. All right, let's take a look at some of our known values. I have them up on the screen already. I know that my object height is 3 millimeters, which is going to be 0.30 centimeters. The object distance is 20.0 centimeters. My radius of curvature is 20.0 centimeters, and my focal length is negative 10.0 centimeters. And remember, the focal length is negative because the focal point is behind the mirror. I want to find the image height and the, I want to find the image distance and the image height. Those are the two things I want to find. So I have the object distance and the focal length. From those, I can use the mirror equation to find the image distance. And to find the image distance, I rearrange the mirror equation like so. I plug in my values for the focal length and the object distance, and that will give me an image distance of negative 6.67 centimeters. Again, it's negative because my image is behind the mirror, and that is a little bit, well, a little bit more than a little bit less than half, but it's less than half of the object distance. So it's a pretty good estimate. All right, now to find the image height. So I'm going to use this form of my magnification equation, and it's the ratio between the image height and the object height, and the image distance and the object distance. Solving that for image height will give me the image height equals the negative of the object height times the image distance divided by the object distance. Plugging my values for those into that equation is going to give me an image height of 0.10 centimeters or 1.0 millimeters.